We're talking about causation, and we've looked at the question of time order precedence and the importance of a strong association. We're going to move on to talk about the problem of taking account of alternative explanations or confounding variables. But to lead into that, I just want to revisit this question of how much information is conveyed by a correlation. And I'm going to be talking about cases where we are dealing with quantitative variables because they are the simplest to explain, really. The methods that we use are reasonably straightforward. Essentially, they are regression methods. So I prepared a set of scatter plots here. What I did is simulate data with different Pearson correlations to give you an idea of what small, medium, and large correlation actually looks like. So the first scatter plot here, this is zero correlation. Okay, this one here. Now, you'll see there's a flat regression line. So the regression line doesn't tell us anything useful. Let's just say, for argument's sake, we've got an independent variable value of, say, 120 there. The regression line predicts that the value of the dependent variable will be 100, which is the mean of the dependent variable. Okay, but it predicts the same thing for an independent variable value of 90 or an independent variable value of 70. So it's not a very useful thing for prediction. It's not frankly useful at all. But when you take the next step, so the next step is we do have a correlation here, but the correlation is a small correlation. So it's a Pearson's correlation of 0.1. And when you look at that, it's barely different to the complete absence of correlation. So for predictive purposes, if there's a correlation of 0.1, it's not telling us very much. If we're interested in an independent variable value of 120, if you look at this, if I just rather clumsily try to draw a straight line, let me see if I can do a straight line there. Control Shift 8. It's not going to work. Okay, this might work. Let's see. Okay. All right. So I can draw a line like that. Now, what you see there is for 120, we could actually have a prediction anywhere between about, I don't know, I guess it's about 90 there, all the way up here somewhere to about, what's that, 140. So somewhere between 90 to 140. So there's a lot of noise there. Okay. If there were no noise, all the points would be on the regression line, and they're not. So that's not giving us. It's giving us a little bit of information. It's telling us that for an independent variable value of 120, we're pretty unlikely to see a dependent variable value of 50. Okay, it's telling us it's going to be somewhere in this range between about 90 and 130 or some, whatever it is there, but not terribly useful. Then we get to a medium correlation. So you can see there the correlation is a little bit more visible in the scatter plot. And if we draw the vertical line, the range is a little bit narrower, not much, slightly narrower. And then if we move over to a large correlation, the improvement is not that great. You know, it is a bit better, but there's still a lot of noise. Okay, we're looking there. We're still looking at about 90 at the bottom end of the range, and you know, there's a handful of sort of outlier points up there, which is still close to 140. And even when we get an extremely high correlation here of what is it, 0.95. Okay, so that's a very high, almost perfect correlation there. The range has narrowed. Let's look at it again. It's narrowed quite a bit. It's now moved up a bit too, but that's just an artifact of the simulation. So the range is quite a bit narrower there. So that's substantially improved, but there's still quite a bit of noise in that. And it's important to bear this in mind, that you know, when you read about correlations or you do some analysis and you get a correlation, not to overestimate the amount of information that it's giving you. Okay, to be a bit pragmatic about this. So as we've seen, we use in this situation with two or more quantitative variables, we commonly use regression, and we will get a statistic from regression which is called R squared. And in the simple case of two variables, the R squared is actually the correlation coefficient squared. So let's look at an example here. For the medium correlation of 0.3, where your R is 0.3, the R squared is going to be about 0.09, or about 9% of the information you'd need to make a perfect prediction. It's a pretty small amount. So the way this is commonly expressed is we say, look, the independent predictor variable, this is for an R squared of 0.25, 25%. The independent predictor variable only accounts for 25% of the variation in the dependent variable. So the question we would have then, if we're interested in causation, is what accounts for the remaining variation, the other 75%? Well, it's possible that it's just a very noisy random process, and that other 75% is just genuinely noise, just error. But another possibility, and this is often the case, is that some of that other 75%, which is not explained by our single predictor variable, is due to some other potential independent variables that haven't been included in the model. Now we're going to look at some examples which come from a data set that was part of it was a study conducted in the 1970s by economists, and what they were actually interested in was they collected data in Boston in the United States, and what they were interested in was the causal effect of pollution on house prices. That was actually what they wanted to investigate. But the data they collected, it's become quite a famous data set. It's used very often for teaching examples and so on. They went to a lot of trouble to collect comprehensive data. They got the data, it mostly came from census data, US census data, but they also obtained data from other sources. So the dependent variable here is median house prices in Boston in the 1970s, and the unit of measurement, the rows, if you like, in the data table, are what are called census tracts. So they are small areas of the city which are assigned to census data collectors. So they might be, I'm not quite sure how big they are, but they might be a few city blocks or something like that. In the data set there is, I think, somewhere between 400 and 500 of these. So the independent variable is the mean, the dependent variable is the median house price in a census tract, in census tracts. And we're going to look first at one independent variable, and that is the number of rooms. So the number of rooms in a dwelling. The information I have about the data doesn't specify exactly what a dwelling is. I guess it could be an apartment or a house, maybe some kind of a boarding house, but the maximum number of rooms seems to be around about 9 or so, or at least the mean number of rooms in a tract. The largest one is just under 9. So what you see there is a plot of these two variables. So the x-axis here is the average, the mean number of rooms in the tracts. So some tracts have a mean of 9, and some have a very low mean of 2 or 3. And the y-axis is the median price in thousands of dollars. So this is thousands of US dollars in 1970, early 1970s, I think it was. And you look at that and you can see, well, this is something a little bit anomalous going on here. There's sort of some outliers there, but basically there's pretty obvious correlation there. The more rooms, the more the house costs. The R is 0.7, the Pearson's correlation, and the R squared is 0.5. So what this is telling us is that the number of rooms in a dwelling, strictly speaking, the mean number of rooms in a census tract gives us about 50% of the information we need to predict the median price of dwellings in the census tract. And as we've done before, we can just write that as a little diagram where we have a line connecting the average number of rooms with the median price. Now, here the convention I'm going to use is I'm going to put in red the dependent variable. For purposes of causation here, there's nothing here is telling us about causation, but you can think about, well, how likely is it that the median price would be causing the mean number of rooms in a census tract? And it seems odd. More likely the other way around, that the mean number of rooms is a causal factor in the price. Now, and we know we have an association. So the issue here now becomes, okay, 50% of the variation is explained by the mean number of rooms. What about the other 50%? Is it just noise, or are there other factors? So now this is, we've got an information flow there. Information about the rooms tells us about the price. Information about the price tells us about the rooms. But nothing, and we've, common sense tells us that if there's a causal direction, would seem to probably be in that direction, but we probably need to go a bit beyond common sense here. What about other factors? Well, we'll look here at another factor. So this is the socioeconomic status of the people who live in these census tracts. And these economists used a measure of socioeconomic status, which I think was essentially the type of work that the breadwinners, as they call them, did. So low socioeconomic status basically meant blue-collar factory workers, manual labourers, people like that. And so this new independent variable is the percentage of dwellings occupied by low socioeconomic status breadwinners. Now, I've done a 3D scatter plot there. So you've still got the dependent variable, the median house price there on the y-axis, and then well, actually, I think that is now probably called the z-axis. It doesn't particularly matter. But we've got the two independent variables here, so the number of rooms as before, and the low SES percentage, and you can see the R squared has now gone up to 0.7. So by adding low socioeconomic status percentage as an independent variable, we have now increased the explanatory power of the model. It's now explaining 70% of the variation in the price. Okay, so we have more information. Now, those sorts of scatter plots are pretty hard to interpret, to be honest. So I'm going to show you another way of representing that data. This is quite a useful technique. It's a bit of a pain to create these in something like Excel, because you basically got to create 6 charts and kind of stick them together, but there's other software you can get that will do this automatically for you. So what is actually going on here is I've divided the data up according to a range of number of rooms. So if you can imagine it like this, we've got 400 and something census tracts for which we have data, so they're the rows in our table. I've created a new ordered categorical variable which has the following values. So 3 to less than 4 rooms, 4 to less than 5 rooms, 5 to less than 6 rooms, 6 to less than 7, and so on. And what I've done is prepare an individual scatter plot for tracts which have those ranges of rooms. So essentially I've sliced the data into 6 slices according to the number of rooms in the tract. So this is a way of getting of flattening 3-dimensional data into 2 dimensions, so you can stick it on a piece of paper. So you still have the dependent variable here, the median house price, and then you have the independent variable low socioeconomic status households percentage. So that's the numbers here on the x-axis. So the way this is laid out is everything, all 6 charts are on the same scale. So you've got the low socioeconomic percentage axis labels there, and you've got them also up there, and you've got them down there. So what do we see here? Well, at 3 to 4 rooms, we've really just a couple of outliers there. There are actually just 2 tracts that have 3 to 4 room dwellings. This is not bedrooms, by the way. This is, kitchen and living room and bathroom and so on. So a 3-room dwelling is a pretty small dwelling. You've got a few more at 4 to 5 rooms, but you'll see that the bulk of them are in the sort of 5 to 6, 6 to 7, and to some extent 7 to 8 room categories. And you can see the correlation's pretty clear there. It's less clear here. This is almost vertical, and it's almost exactly vertical up here. But so what this is showing is that in each of these sort of most common ranges of numbers of rooms, there is a negative relationship between the percentage of low socioeconomic status households and the median price. Okay, so this kind of makes pretty clear what's going on there, that there's a positive relationship, which we can sort of see in the fact that these clouds of points are, putting aside this first couple of outliers here, they're kind of drifting upwards as we increase the number of rooms, and then we can see this very striking negative relationship based on socioeconomic status. So that's so what we have there is, let's see if we can, we have a, okay, so we can do an initial sort of visualization of that here, that the average number of rooms affects the median price, or sorry, let's be clear here. there is a correlation or an association between the average number of rooms and the median price, and similarly there is a correlation between the percentage of low socioeconomic households and the median price. This is a positive relationship and that is a negative relationship. So we've got two information flows there: median price, average number of rooms, and median price, low SES households. Now, so in terms of causation, we've now identified two factors or variables that might be causal, but things could get more complicated. So is there an association between low SES and the number of rooms in the dwelling? That's a good question. Well, we can test this. We can add it to the model. Okay, so without worrying too much about the sort of mathematical mechanics of this, I have put the regression equation there if you're interested, but don't worry too much about the detail of that. It turns out though that if we add it in, it increases the R squared even further. We now have an R squared of 0.8. So what we've added is what's called an interaction. So there is an interaction between low SES households and the average number of rooms, and we may want to think about what that we can think about what that means in the real world. It could be, it often is in many parts of the world, the case that low SES households have more children, they have larger families, or they may have larger extended families, and so they need to live in dwellings with more rooms. So just to summarize what this is all about, what we need to be doing, one of the things we need to do when we're trying to sort of pin down causation, is we need to start thinking. There needs to be a strong association between whatever we think is our causal variable and the caused variable, but we also need to take into account other factors. So the first thing we have to do is try and identify what the other factors might be. And what we've done here is we've identified two factors, the number of rooms and low socioeconomic status, which affect median price. And we've also identified that there is an interaction between low socioeconomic households and the number of rooms in houses. So the story becomes more complicated, and this is typical. This is typically what we face when we start trying to actually pin down causal relationships by analyzing data. I'm going to stop this here now. I'm going to give another example in the next video.